Welcome back, class. Today we're going to start connecting all of these generating function things back to partitions. So we're going to review some things that we've done before, but now in this brave new context of generating functions. So remember this P of n business. This is the number of partitions of n. And remember that a partition is just a list of numbers that sum to n. So for example, if n is 5, then we're looking at things like, well, 5 is a partition of 5, and 4 plus 1, and 3 plus 2, and 3 plus 1 plus 1, 2 plus 2 plus 1, 2 plus 1 plus 1 plus 1, and last 1 plus 1 plus 1 plus 1 plus 1. So that is 1, 2, 3, 4, 5, 6, 7. So P of 5 is 7. And we've talked about lots of flavors of partition before, but this is sort of the general partition. And remember, the order doesn't matter, so it's just easier if we generally write them in descending order. So 2 plus 2 plus 1 is not different than 2 plus 1 plus 2 for purposes of these. So I want to talk today about the generating function of this partition function. So namely, we're going to call this e of x. This e is for Euler, because he was the first person who considered this. And so this is the sum, as n goes from 0 to infinity, of p of n times x to the n. If you want p of 0 is 1, I'm tossing that in so that I don't have to add a minus 1 somewhere in this formula. Okay, so this sort of lines up very cleanly with the sorts of things we've been doing. In fact, if you want, you could think of a partition as making change for n cents, except instead of just having pennies and nickels, you have 1-cent coins, 2-cent coins, 3-cent coins, 4-cent coins. In fact, you have coins going all the way up as high as you possibly want. And so this thing, when I go to write it down, this is actually going to be a product. And so each term is going to correspond to how many copies of one particular number show up. So the first line will be how many ones we use. So we'll get that. And so this is no ones, 1, 1, 2, 1, 3 ones, and so on. This is how many 2s we use. Then how many 3s we use. And then so on. So I'll have to do that for 4s and 5s and 6s. And so again, just to make sure we're super clear, this line is telling me I'm getting, say, 3 worth of 1s, which would mean I'm using 3 1s. This x to the 6th would say I'm getting 6 worth of 2s, which would say I'm using 3 2s. This x to the 6th is saying I'm getting 6 worth of 3s, which would say I'm using 2 3s. So the power in particular is not the number you're using in the partition, it's the amount you're getting from using that number in the partition. Okay, so if I continue this onto the next page over here, we can again use our geometric series formula, which is our favorite formula for this week, to rewrite this, that this is 1 over 1 minus x times 1 over 1 minus x squared times 1 over 1 minus x cubed times, and then so on forever. Now I can rewrite this, and this is sort of like an infinite sum, except it's an infinite product. So I can rewrite this in capital Pi notation. And so I'll write this down and then I'll say what it means. This is the product as I goes from 1 to infinity of 1 over 1 minus x to the I. I'll remind you, That is our Euler of x. And so what this means, this is exactly like the giant sigma, except that the sigma is saying you take all of these things and you add them together. This is saying you take all these things and you multiply them together. And in fact, the reason why we use these symbols is because this is a sum, and so sigma is the Greek letter S. This is a product, and pi is the Greek letter P. Okay, so this is a formula for our generating function for regular partition numbers. But I wanted to talk about a couple other types of partitions and a couple other things. So we're going to first write down some generating functions and see what we can do with them. So let's talk about the Q partitions. So a Q partition, this is a partition into distinct parts. Of n into distinct parts. So if you look back over here to the ones for 5, the ones with distinct parts are that one, that one, that one. And those are the only ones with distinct parts. So Q of 5 is 3, for example. And so this is saying I'm never using more than one of a particular number. Okay, so of course, what's the question going to be? Well, the question's going to be if I take Q of x, and I go ahead and let this be the sum as n goes from 0 to infinity of Q of n times x to the n, how can I write this down as some sort of product of some sort of polynomials or power series or whatever? Okay, I'm going to suggest here, because this is similar enough to what we've been doing, pause this for just a second, and then after you've thought about it, make sure you could do this question, and then we'll do it together. Okay, so pause it, think about it. Okay, 3, 2, 1. Okay, so let's do this. So again, like before, I need to have a term for each digit. So a term for 1s, a term for 2s, a term for 3s, and so on. But the difference is, when I think about how many 1s I can use, I actually only have 2 choices. I can either use the 1 or not use the 1. So that's use the 1, that's don't use the 1. Likewise for 2s, I either have a 2 or I don't. And I either have a 3 or I don't. And so on down the line. Oops. Okay, and so that's just going to be, at the end of the day, that's the product as I goes from 1 to infinity of 1 plus x to the I. And that is my Q of x. Okay. Another flavor we talked about. We talked about partitions into specifically odd parts. So O of n, this is going to be the number of partitions of n into odd parts. Okay, and so again, if you want to go back and play this game here, the ones for 5 were this one and that one and that one. So there were 3 of those. Okay. I won't give away the punchline yet, but if you have a very good memory, you'll remember what the punchline of this is going to be. But O of 5 is 3. And so I want to now write down the generating function for this. So O of x, that's the sum as n goes from 0 to infinity of O of n times x to the n. And so this is going to be, well, I can use ones, so I can use any number of ones. Okay. Again, note it's okay that this x squared is even, because that's corresponding to saying I'm using two ones, and 1 is odd, even if I have two ones. I can't use any 2s, so I skip straight to 3s, and then to 5s. And so on. Okay, but I can, of course, rewrite this using, again, our favorite formula in the universe. So this is 1 over 1 minus x times 1 over 1 minus x cubed minus x to the 7th times dot, dot, dot. Okay. Now, you might be inclined to notice that there seem to be some missing terms. There's no, if I look at the denominator here, there's no 1 minus x squared, no 1 minus x to the 4th, and so on down the line. So I'm going to put those in just to try and clean this up a bit. So, of course, I can't just add them. So I'm going to add in a 1 minus x squared in the denominator by also putting a 1 minus x squared in the numerator. And then times minus x cubed times and I'll go ahead and go out to the same place that I went before. Okay. And this is going on forever. Okay. I'm going to rewrite this just by suppressing all of the 1 times, because multiplying by 1 isn't doing anything for me. So I'm going to go back and put the 1 minus x squared now over the first term. And so if I continue now, there's a 1 minus x squared here times, and so my next denominator here is a 1 minus x squared. And what is my next numerator? My next numerator is a 1 minus x to the 4th times, and so my next denominator here is a 1 minus x cubed. My next numerator is a 1 minus x to the 6th times, and then so 1 minus x to the 8th, 1 minus x to the 4th from before, and so on. Okay. But I can simplify 1 minus x squared over 1 minus x, because 1 minus x squared is a difference of squares. So this is 1 minus x times 1 plus x, but now I'm dividing it by 1 minus x. So this is just 1 plus x. Okay, but the same is actually true here. 1 minus x to the 4th is also a difference of squares. So this is 1 minus x squared times 1 plus x squared. But that's divided by 1 minus x squared. So this is a 1 plus x squared here. And then this is a 1 plus x cubed here. This is a 1 plus x to the fourth. Okay, again, all I'm doing here is using the difference of squares factorization formula over and over and over again, because every numerator here is a difference of squares. And as it happens, every numerator here happens to be a difference of squares where one of the factors is the thing in the denominator. And so then I get exactly this. But we've seen this before. Namely, this is exactly the generating function that we wrote down for q of x, the number of partitions into distinct parts. And so what we've said here, what we've proven, is that in fact, the generating function for the number of partitions into odd parts is the same as the generating function for the number of partitions into distinct parts. And what does that mean? That means that for every n, the number of partitions of n into odd parts is the same as the number of partitions of n into distinct parts. And so we've actually given here a completely different proof of a result that we did give a combinatorial proof of in class, by the way, that for all n, this thing I called q of n is exactly equal to O of n. All right, we'll wrap up this video here, but I promise in the next video, we'll do more of this. So we'll come up with more ways of writing down generating functions and nice formulas for them, and then we'll try and deduce the sorts of things that we can do with them. All right, but until next time, be well.